Today we're going to be talking about section 3.3. 3.3 is really about this idea of concavity and inflection points. So if a function is concave up, then that means on the interval that it's concave up, its first derivative is going to be increasing. Now let's think about that for a second. If I can get my chalk opened. If we consider the function f of x is equal to x squared. Its first derivative is going to be equal to 2x. Well, notice the derivative here is increasing, right? It's going from negative values to constantly larger values, right? If we were to take the second derivative of our function, so the first derivative of that first derivative, we would get something that looks like this, right? And in general, anytime a function's increasing, that derivative will be positive. So when we say the first derivative of a function is increasing, we're saying the second derivative is positive. Make sense what I mean? Yep. Notice here too that our original function x squared, it's concaved up and it looks like a bowl, right? This is what it means to be concaved up. If you were to take part of it that's concaved up, rotate it about some single point and form a bowl, will it hold soup in it? If not, then it's concave down. So as an example of what I mean, concave up, we can put soup in here, right? Concave down, we're dumping it on the floor. I know that's kind of a trite way of describing it, but it kind of effectively gives us an idea of what we're looking at. Having said that, check out what's happening to the tangent lines. The tangent line to this function is slowly increasing in slope, right? Here, it's slowly decreasing in slope. We start off with a positive, we go negative, we go more negative. Up here, we start off with a negative, we go positive, we go more positive, right? So if we want to test for concavity, using this logic that I just drew up on the board, we can check out what's happening to the second derivative on an interval. In particular, if the second derivative is positive, then we're concaved up. If the second derivative is negative, then we're concave down. And to test for this, we're going to check out places where our second derivative is 0 or it's undefined. So it's a little bit like that first derivative test we were working with the other week, or I guess last week. But now it's second derivative, and it's going to tell us something about the overall shape. Not just if we're increasing and decreasing as a function, but if we're concave up or concave down. So as two examples of this, we've got x squared, which I already drew on the board. The original function, x squared, the second derivative is equal to 2. We're concaved up. In the second example, we've got the square root of x. The second derivative is negative 1 over 4 x raised to the negative 3 over 2 power. Well, check out what the square root of x looks like. If we were to rotate this and make a ball, we'd be dumping out everything onto the floor. Also notice that the negative out front, it's going to make everything negative, right? Because the square root of x is always positive. So negative times that, it's always negative. All right, so now we've got an example that we can work on as a class. We've got 6 divided by x squared plus 3. Our function of x is equal to 6 divided by x squared plus 3. The first derivative is high d low or low d high. What's the derivative of quotients? Low d high, right? Minus high d low divided by the square of what's below, right? So low x squared plus 3 times the derivative of 6 is 0 minus high times the derivative of what's below, that's 2x, all divided by the square of what's below, x squared plus 3. So this thing is going to come out to be negative 12x, oh, the square of what's below. I forgot to put the square out. Divided by x squared plus 3 squared. Everybody agree with that? Now, taking the second derivative, low d high, x squared plus 3, that quantity squared, times negative 12 minus high d low, that's going to be negative 12x. The derivative of this is going to be 2 times x squared plus 3 times the derivative of what's inside. Well, that's just going to be 2x, right? All divided by x squared plus 3 to the 4th power. Everybody agree with me so far? So checking what we've done thus far. The first derivative comes out to be negative 12x, x squared plus 3, exact quantity squared. The second derivative then comes out to be x squared plus 3 squared, which is what we've got there, times negative 12, we've got there, times negative 12x, times 2, times x squared plus 3, times 2x. All divided by x squared plus 3, the quantity to the fourth power. Once we simplify it, we're going to get to this last form, 36 times x squared minus 1 divided by x squared plus 3 to the third power. Now, a few things are going to happen here. The first thing we want to do is we want to set f double primed of x equal to 0, right? When is this going to happen? This is going to happen whenever x is equal to -1 or 1. Agreed? Folks at home, you with me on this?
Yeah.
Awesome. All right, so we've got this implies x is equal to plus or minus 1. Now the next question is, when is this thing undefined? Which is the same as asking when x squared plus 3 is going to be equal to 0. Well, there's no value we can put in for x that will make x squared -3, right? So it's never undefined. So all we need to concern ourselves with is this plus or minus 1. Yeah? Having said that, we can now bust out a nice little table. And consider x less than -1, x between -1 and 1, and 1 or an x greater than 1. Now in this interval, we're going to choose our test points. Let's use 2, 0, and 2. Just like what they've got. -2, 0, and 2. When we put in -2 here, we're going to get 4 minus 1. It's going to give us 3, a positive number. This will always be positive, yeah? So this is going to be positive then. Agreed? So F double primed at -2 is greater than 0. Now when we put in 0, 0 squared is 0. We're going to get -1 out of this, right? -1 times 36 is -36. This thing's always positive. So we're going to end up with -36 divided by a positive number. So it's negative. F double prime at 0 is less than 0. And then testing at 2, we're going to run into the same thing we ran into here, right? So, what did I change? Doc. So F double prime at 2 is going to be greater than 0. And we can conclude that here we're concave up, down, up. Now, comparing that to the graph of our function, check out what happens if we were to cut our graph at -1 and 1. If we were to spin this interval about, we'd have a ball that's doping things out. If we were to spin this interval about, we'd have a ball that's holding things. Similarly, a ball that's holding things, right? So we're concave up, down, and up again. Is everybody cool with this? Holy shit, that was not what I wanted it to do. Go back to normal view. Yeah, there, dope. Now, having said that, something else I want to point out. These points where we change our concavity, these are the points where we go from concave up to concave down. But these points are neither concave up nor concave down, right? Because they're at that point of change. They're called inflection points. Go back to normal view. An inflection point is just that. It's the point where we go from concave to up to concave down or down to up. And the test for them is simply just to look when our derivative is 0 or undefined. Having said that, well, I'll get to that after a while. So as another quick example, let's consider the function x to the 4th plus x to the 3rd minus 3x squared plus 1. Taking the first derivative, pretty straightforward. Taking the second derivative, we can factor things out. And factoring it out, we're going to get 6 times the quantity, 2x minus 1, times the quantity, x plus 1. These two factors will give us our zeros, right? Again? Wow. That was another earthquake for those of y'all at home. So these two factors will give us our zeros. Notice here, if x is 1/2, we have a 0. And here, if x is -1, we have a 0, right? So our inflection points must be, presumably, if they're going to be anywhere, at either -1 or 1/2. Make sense? Now looking at our graph, we can see that. We have the inflection point here and here. This whole thing is concave up. This thing is concave down. This thing is concave up, right? So yesterday I was in my office when that 4.0 hit. Let me just say, being on the 3rd floor of a building wasn't my idea of fun. I was not expecting that. I guess it could have been worse. I lived on the West Coast. So just as a point of observation, just because you have a second derivative that's equal to 0 doesn't necessarily mean you're going to have an inflection point. So for example, x to the 4th power. The second derivative here is going to be 12x squared, right? So that means when x is equal to 0, we're going to have a second derivative that's 0, but it's not an inflection point. So we're going to have to do a little bit of digging to make sure these are in fact inflection points. And to do that, we can look at these tables, right? If we go from concave up to concave down, or down to up, then it's an inflection point. Is everybody cool with that? Having said that, checking for relative mins and max, given that we have a critical number at C, so let's remember what that is. That's whenever our first derivative is equal to 0. If our second derivative is greater than 0 on some interval, including C, then we must have a relative min at C. And if x is less than, if our second derivative at C is less than 0, then it must be a relative max. So to look at what I mean, what I'm saying here. Here, we're concaved up, right? We have this point somewhere around here where our first derivative would be 0, right? In this interval, in this whole chunk, our second derivative has to be positive, right? Well, since it's positive, we know we're concaved up. And since we have a critical point in that interval, it must be then that that critical point is a min. Make sense? So we flatten out, and then we go back up in either direction. Whereas if we're concave down, we're increasing, flatten out, decreasing, or my mistake. We're decreasing, flatten out, decrease, right? So again, same idea. Now, in a minute, we're going to talk about absolute maxes and absolute mins. So I want to make a point of saying this is a relative max, this is a relative min. What a relative max and a relative min is if you were to jiggle your x value, consider a small collection of x values on either side. In the case of a relative max, every other x value in that small collection will be less than what your function is at c. Similarly, if it's a min, then f of c will be smaller than all the other x values around c. Does that make sense? So let's find the relative extremas of this function here. What we've got, I'll write it out on the board. You know what we need? Self-erasing boards. How awesome would that actually be? If I have any engineering students, please make a self-erasing board. I'll give you extra credit for it. All right, so we've got this function, negative 3x to the 5th plus 5x to the 3rd. The first derivative of this is going to be negative 15. That was another earthquake for those of y'all at home. We've got negative 15x to the 4th plus 15x squared, right? So we can pull out a 15x squared. Pulling that out. We're going to get, this is 1 minus x squared, right? So our critical points here are going to be at x plus or minus 1 and x equal to 0, right? Because if x is equal to 0, this term becomes 0, or this factor rather becomes 0. And if x is equal to 1 or minus 1, this factor is going to be 0, right? So we know our critical numbers are going to be x plus or minus 1 and x equal to 0. Now, we want to take and find the second derivative of this. The second derivative is going to be negative 60x cubed plus 30x we can factor out the 30x. Agreed? And when we do, we're going to get 30x times 1 minus 2x squared. Yeah. So in order for this to be 0, all we need is x to be 0 here. However, in the second factor, we need x squared to be equal to 1/2, right? So x is going to have to be 1 over the square root of 2, plus or minus, right? So what I'm saying is, the first one's pretty straightforward. We have 30x. The second one, though, we need to do some work on. Subtracting 1 from both sides. We're going to have negative 2x squared is equal to negative 1. Dividing both sides by negative 2, we get that x squared is equal to 1/2. So x is equal to plus or minus 1 divided by the square root of 2. Right? So for the sake of workroom, all right, what we're going to do now is break our interval up into, what is that, 4 different parts? The first one's going to be x is equal to negative 1 over square root of 2 for every x less than that, right? I'll write that in a second. Then 0, then x is equal to 1 over the square root of 2. So this gives us the intervals. Negative x to the negative 1/2 power, right? X is less than, my mistake, 2. The negative 1/2 power, right? Then here, x is between 0 and negative square root of 2 over 1, or 1 over the square root of 2. Then x is less than then x is greater than 1 over the square root of 2. Is everybody with me on this? All right. This interval where x is less than negative 1 over the square root of 2, this interval is going to contain 1, right? Or negative 1, I mean. This interval does not contain that. This interval contains nothing. And this interval contains 1, right? And then c is equal to 0, we can write up here, since it sits here. These are going to be 2 natural test points to use. Since our critical numbers sit inside of these intervals, why don't we go ahead and use them? Does that make sense? Now, here, we need to choose some values that are going to fit inside these intervals. What values might fit in here? What do you all think? Well, the square root of 2 is going to be close to 1, right? So I'm going to jump ahead just to, well, they don't actually test that. Cool. All right. So what value might we use? Anything in particular jumps out at y'all? 1/2? Yep. Why not, right? Wait, can't use 1/2, but we can use 1/4. Yeah? And we can use 1/4 over here too. So here, when c is equal to -1, our second derivative is going to come out to be -30 times 1 minus 2, right? 1 minus 2 is going to be -1. -30 times -1 is going to give you 30. So f double prime at -1 is greater than 0. So we're going to be concave up. At 1, we're going to have 30 times -1, right? So that's going to be -30. Which is less than 0. So we're going to be concave down. Now the question is, do we need to test these 2 points? What do you all think? Let's look just at the graph of this thing to see if we can pull out some intuition. That is not what I wanted to do. Go to the next slide. Here. All right. So just because of this, automatically we know this is going to have to be a min, right? This is going to have to be a max. Turns out our second derivative is 0 here. So best case scenario, we have an inflection point. Worst case scenario, we have a discontinuity. Everybody agree with that? So we can't actually test when x is equal to 0. Does this make sense what I mean? So we can't determine then if it's a max or min using this test. Does that make sense what I'm trying to say here? So in other words, because x is equal to 0, our second derivative is equal to 0 whenever x is equal to 0, which is also a critical number, then the second derivative test fails. So to recap, we found our critical numbers to be -1, 0, and 1. We found those by looking at the second derivative and setting it equal to 0 and finding those x values associated with that, right? Then we said, all right, let's find the second derivative now. Let's set that thing equal to 0, just so we can break up these intervals like this. Hey, this thing's going to be a relative min, this thing's going to be a relative max, but at 0, our second derivative is 0. So the test fails. Also notice it's just worth noting, I feel like here, that F double prime at -1/4 is going to be concave down. Whenever F double prime is evaluated at 1/4, it's greater than 0, so this is going to be concave up. But like I said, the test fails when we try to put in 0 for x. And that's because it's an inflection point. And inflection points can neither be mins nor maxes. Is that cool with everybody? So notice if we really wanted to here, we could go through and try to rediscover what the graph of our function is going to look like. We could approximate it if we wanted to. All right, so what is all of this for? Like, when are you going to use it? Well, we can start defining diminishing returns. So what's a diminishing return? In your own words, what do you think a diminishing return is? People at home, what do y'all think a diminishing return is? In your own words.
The amount of money you get back is getting smaller?
Kind of, yes.
Like your return on investment is getting smaller?
Yes, the return on investment is getting smaller. The amount of return that you're going to get for every dollar you put in starts to contract at this point. So another way of looking at this is to say it's an inflection point, right? So let's look at what's happening here. For every dollar we put in, the increase is going to be large, right? And it's going to get larger as we approach C. Beyond that, though, it's going to start contracting. So for every dollar we put in now, once we pass C, that return starts to contract. It starts to diminish. So a point of diminishing return is nothing more than an inflection point. Having said that, I want y'all to take about 2 minutes and try to solve this on your own really quick. So, how many people got 20 as an answer? X is equal to 20. That's the X value in which your returns start to diminish. Anybody?
I don't.
So let's see why this is. Going through, just really quickly looking at the graph of this thing, it's going to be a polynomial with the highest power being 3, right? So we know it's going to kind of be this humpy, snake-looking S-shaped thing. I don't really know how to even begin to describe this. That shape, that is. So, looking at it, we can see that for the first part, we're concave up. For the second part, we're concave down. So our point of diminishing return, we know it's going to be an inflection point. We know it's for sure going to exist, right? That's the first thing we should probably ask ourselves here. Are we even going to have a point of diminishing return? Having said that, after we take the first derivative, we're going to go on and take the second derivative. So this thing equal to 0. And solve for x. When we solve for x, we get 20. Now we're going to go back and throw 20 back into our original function to solve for y. Because after all, we should probably know that, right? Like how much we're going to get out of it at our point of diminishing return. That's going to be some useful information for us as a business. So once we find that our inflection point is likely to be at 20, we want to test on the interval 0 to 20. Then we want to test on the interval 20 to 40. We find that it is, in fact, diminishing return. So that is to say, it's not enough to just stop here. We have to go through and use that table type idea and test our two different intervals. Does that make sense? just so that we know that we change concavity. Otherwise, it's not an inflection point. Yeah. And just to really hammer in this point, let's consider 1 over x squared. This function, if we were going to graph it, it's going to look something like this. Taking that first derivative, this is the derivative of x to the negative second power, right? So the power rule applies here. This thing's going to come out to be negative 2 over x to the third, right? Now doing it again, f double prime of x is going to be the derivative of negative 2 over x negative third power, negative 2 times x to the negative third power is what I'm trying to say. This thing is going to come out to be 6, 1 over x to the fourth, right? Everybody agree on this? Well, this thing is undefined at 0. Notice 0 is not an inflection point here. It's a discontinuity, right? So because it's a discontinuity, the test would fail. Agreed? Notice what else happens here. This also occurs when our critical number is 0. So this is something to be mindful of. This is one of the reasons why it's convenient to go ahead, once you already have your first derivative, find your critical numbers. Because if your critical numbers are equal to your second derivatives, it tells you that you either have an inflection point or a discontinuity. Make sense? Meanwhile, if they're different values, then this will tell you, these critical numbers will tell you if you have a max or a min, a relative max or a relative min. Cool with that? Yep. All right, having said that, I'm sorry for holding y'all 10 extra minutes. Y'all are free to go. If you all have any questions, I'll stick around.
Thank you.
Not a problem. Have a good one, guys.